Okay, get ready, because we are diving deep today into the quantum realm, specifically quantum entanglement. You've been looking into this idea, right? Where particles are linked, but in a way that makes space and time feel, well, a little less solid than we usually think of them.
It's a concept that really pushes against some of those basic assumptions we have about how the universe works.
Absolutely. We've got excerpts from the Wikipedia article about quantum entanglement, gives us a good starting point, and then we get to dig into your notes on the topic. Looks like some really interesting questions in there.
Always love to see where someone's curiosity takes them.
So let's start with the definition. What is quantum entanglement exactly?
At its core, quantum entanglement happens when two or more particles become so closely linked, so intertwined, that they share the same fate, even when they're separated by huge distances. And what makes this so incredible is that when you measure the state of one of these particles, it instantly affects the state of the others that are entangled with it, no matter how far apart they are.
Okay, and that's where things start to get really wild, really complex. I've seen the analogy of a pair of gloves used to try and make this a bit easier to picture. Like one glove is red, one is blue, and you send one to a friend on the other side of the world. The moment you open your box and see, oh, it's the red one, you instantly know your friend has the blue one, right?
It's a good visual, but it's important to go beyond that simple analogy if we want to really grasp the strangeness of entanglement. Because we're not talking about fixed properties like the color of a glove. Instead, with these particles, we're dealing with something called superposition.
Superposition.
Right. It means these particles exist in multiple states at the same time, all at once, until we measure them.
So it's not like the gloves were always one color or the other, and we just didn't know until we looked. It's more like the act of looking, of observing, forces them to choose a color.
Exactly. Before we measure them, these particles exist in something we call a wave function. This wave function describes every possible state they could be in, all at once. But when we measure a particle, its wave function collapses, and at that instant, it chooses a single definite state. And here's the entanglement part. The very moment one particle's wave function collapses, any other particle entangled with it, its wave function collapses instantly as well. It doesn't matter if they're light years apart.
So this isn't about information traveling faster than the speed of light, is it? It's about a connection, a correlation that seems to ignore distance altogether, like it doesn't even exist.
Exactly, and that's where a really crucial piece of this comes in, Bell's theorem. Back in the 1960s, a physicist named John Bell, he came up with a way to actually test whether these correlations could be explained by something simpler, something more straightforward.
Like, maybe these entangled particles actually had some hidden instructions all along, some kind of code telling them what state to be in, so it only seemed random.
That's the idea. And Bell's theorem was brilliant. It gave us a way to actually test that hidden variable theory out.
Hmm.
And the experiments showed definitively that Bell's theorem holds true. These correlations, they couldn't be explained by hidden variables. Something far stranger, something far more profound was going on.
So Bell's theorem kind of threw a wrench into our classical physics understanding of things, didn't it? Like, we're dealing with a universe that's inherently non-local, where things can be connected in ways that seem impossible based on everything we thought we knew.
Which opens up some pretty mind-bending philosophical questions.
Right.
But we'll get into those in the next part of our deep dive.
Okay, so we've laid out the groundwork, right? Quantum entanglement, it's real. Bell's theorem, that's solid evidence. But the implications of this, like a universe where distance might be more like, I don't know, a suggestion box than an actual rule, that's huge. Like we've bumped into a whole new layer of reality or something.
It really is a profound shift in how we see things. Entanglement suggests this interconnectedness at the core of the universe, in ways we're just beginning to even imagine. It makes you question those fundamental concepts, cause and effect, locality, maybe even the nature of reality itself.
And that's where my brain starts to, I don't know, short circuit a bit. Like, what does it even mean for the universe to be non-local? I mean, we experience distance all the time. So how do we square that with this idea, this entanglement thing where everything's connected at some deep level?
That's the million-dollar question, isn't it? And it's one that physicists, philosophers, they're all still wrestling with. One way to think about it, maybe our everyday experience of space and time, it's just that, an experience. Maybe it's something that emerges from a much deeper, more fundamental level of reality, where entanglement is the standard, the norm. Like, imagine a tapestry. You look at it from far away, you see these threads, these patterns, but if you get up close, you realize it's all woven together, interconnected, and that's what creates the bigger picture we see.
So you're saying maybe entanglement is like the underlying, I don't know, the fabric of the universe, and our feeling of separateness is just that, a feeling, not the whole story.
It's an interesting thought, and it leads to even more questions. Like, what's the role of measurement in all this? We've said that measuring a particle collapses its wave function, but what even is a measurement in the quantum world?
Yeah, that was on my mind too. Is it the device we use? Or does it have to be like a conscious observer? In my notes, I've got the measurement problem circled about 100 times.
Ah, yes, the infamous measurement problem. A real thorny issue in quantum mechanics. Gets right to the heart of how our classical world comes out of this quantum stuff. There are a bunch of different interpretations, but the Copenhagen interpretation, that's one of the most, well, traditional ones.
Break it down for me. What's the Copenhagen take on this measurement problem?
Basically, it says that the act of measuring, that's what makes the wave function collapse. But it doesn't really say how it collapses or what counts as a measurement in the first place, which is why there's so much debate.
So kind of sidesteps the issue a bit.
Some might say so. It leaves open this possibility that maybe, just maybe, consciousness itself plays a part in collapsing the wave function, which takes us into some pretty wild territory, philosophically speaking.
Okay, now we're getting into the really trippy stuff. So any other interpretations that try to like tackle this measurement problem head on?
Absolutely. The many worlds interpretation, that's another popular one. It suggests that every time there's a quantum measurement, the wave function doesn't collapse, it branches, creates multiple universes, and each possible outcome of that measurement, it happens in its own separate reality.
Wait, hold on. Multiple universes. We're talking like every time we observe a particle, we create a whole new reality.
That's the basic idea, though it gets, well, a bit distorted in pop culture sometimes. It's important to remember the many worlds interpretation. It's just that, an interpretation. We don't have any definitive experimental proof for it or against it, which is part of what makes quantum mechanics so fascinating.
Feels like we've opened up this whole Pandora's box of mind-blowing possibilities. But before we go too far down that road, something a little more grounded. All this entanglement stuff, non-locality, multiple universes, it's wild. But what about real-world uses? Can we actually do anything with this knowledge?
Great question. Brings us back down to earth a bit. We're still in the early stages of really understanding entanglement. But the potential applications, they're incredibly exciting. Quantum computing, that's a big one, creating a lot of buzz.
Okay, quantum computing, I've heard the term, but honestly, not totally clear on what makes it different from the computers we use every day.
So think about it like this. Regular computers, they store information as bits, right? Each bit is either a 0 or a 1. Quantum computers, they use qubits. And these qubits, they can be in that superposition state, meaning they can be a 0, a 1, or both at the same time.
Whoa.
And that's the key. It lets quantum computers do calculations way, way faster than our regular computers and tackle problems that would take classical computers, even the most powerful ones, practically forever.
So we're talking about like using superposition to completely change how computers work. That's insane. And I'm guessing entanglement plays a part in this too.
Absolutely. Entanglement is how we connect these qubits together, which is what gives quantum computers that huge boost in power. When you entangle qubits, they're linked. Their fates are tied together. Anything you do to one instantly affects the others. That interconnectedness, that's the magic ingredient.
This is seriously blowing my mind. Any other possible uses for entanglement besides these superpowered computers?
Quantum cryptography is another big one. Tons of potential there. It uses entanglement to create these unbreakable encryption keys, making sure communication is totally secure. Because if anyone tries to listen in, to eavesdrop, even a little, it'll disrupt those entangled particles. So the sender and receiver, they'll know instantly that someone's trying to snoop.
Wow, unbreakable codes. That's incredible. Feels like we're on the edge of a whole technological revolution, all thanks to quantum entanglement.
It's still early days, but the possibilities are massive.
Mm-hmm.
And it all comes back to this one mind-boggling concept, a concept that challenges our whole understanding of how reality works.
I'm 100% hooked on this stuff.
Yep.
So in this part of our deep dive, we've gone deep into the philosophical side of a non-local universe, wrestled with this measurement problem, and even touched on the real-world applications, things like quantum computing, quantum cryptography.
A whirlwind tour of some of the most fascinating and some might say frustrating concepts in physics.
It really has been, but we're not done yet. In our final part, we're going to get into your notes specifically. Really dig into the questions you've been pondering about this whole mind-blowing phenomenon. All right, so we're back and ready to dig into your questions about quantum entanglement. We've covered some seriously complex stuff, from Bell's theorem to that whole many worlds interpretation, but now let's bring it back down to Earth, your Earth. In your notes, there's some really sharp questions showing you're really grappling with these ideas.
Always fascinating to see how these concepts resonate, how they spark individual curiosity.
Exactly. And one thing that keeps popping up in your notes is this idea of consciousness. Like, what role does consciousness play in quantum mechanics? You even highlighted that, quote, the universe is not only stranger than we imagine, it is stranger than we can imagine. That feels very relevant here. So where's your head at right now on this whole consciousness and entanglement connection?
That is a question that's been kicking around for decades, a real source of fascination, and let's be honest, some serious debate too. Physicists like Eugene Wigner, they've suggested that consciousness might be the missing piece in this whole measurement problem we've been talking about.
They're saying it's not just about the measuring device itself, but the actual mind of the observer that's playing a role.
That's the gist of it. They argue that it's the act of conscious observation that causes that wave function to collapse, that forces the particle to choose its state.
Okay, but that's a pretty radical idea when you actually stop and think about it.
It really is. And it's important to point out there's no real scientific consensus on this yet. It's definitely veering into more speculative territory, interpretive, but the questions it raises are fascinating, right? If consciousness is involved, what does that say about the very nature of reality? Does it mean our minds are somehow, I don't know, woven into the fabric of the universe in ways we don't understand yet?
Okay, now that's where my brain starts to hurt a little. And it makes me think about some of the connections you've drawn in your notes, like the implications of entanglement for human connection, even things like intuition, psychic phenomena. You're making these really interesting links between what's happening at the quantum level and our everyday experiences.
Well, one of the most mind-blowing things about entanglement is that it challenges this idea we have of separateness, this fundamental assumption. If particles can be linked in such a deep way, no matter how far apart they are, you have to wonder, right? Could there be other ways we're all connected that we haven't even begun to understand?
So maybe entanglement is just the, I don't know, the tip of the iceberg when it comes to how interconnected everything really is. And some of the things we call paranormal, those experiences we can't explain, maybe they're just examples of quantum principles at work on a larger, more complex scale.
It's a tempting thought, isn't it? But it's crucial to approach these ideas with a good dose of skepticism, too. Science, it thrives on evidence, on rigorous testing. And while entanglement does give us whole new avenues to explore, we have to be careful about jumping to conclusions.
For sure, for sure. Like Carl Sagan said, extraordinary claims require extraordinary evidence. But I think it's equally important to stay open to the possibility that what we know about the universe right now, it's not the whole picture. Entanglement is proof that the universe is full of surprises. Who knows what other mysteries are out there, just waiting for us to uncover them as we keep exploring this quantum realm.
Exactly. And your questions, they highlight how powerful curiosity is.
Yeah.
Questioning what we think we know, that's what leads to new discoveries. Entanglement, when you really get down to it, it's a reminder that the universe is far stranger, far more wondrous than we could have ever imagined.
Beautifully put. So as we wrap up our deep dive into quantum entanglement, I want to leave you with this. We started with what seemed like a simple question. What happens when particles get entangled? But as we've seen, that one question has sent us tumbling down this rabbit hole of mind-bending ideas, philosophical dilemmas, even potential technological revolutions. It's a journey that forces us to stretch our minds, get comfortable with uncertainty, and never, ever stop asking, what if?